sorry, I didn't have the time to write this before. So first of all, thank you to the organizers for setting up this meeting and for the chance to talk. As Graham said, I'm going to talk about Jordan type of Artinian algebras. I'll spend most of the talk trying to define it. Some other invariants that we have, and if I have the time, some applications. And I'll use this talk also to present two of the problems that I'm proposing for the working groups afterwards. This is well, I'm going to report on work mainly with Tony Arubino, Chris McDaniel, and Johannes Steinmeier. But I must say that the problems themselves are the result of a lot of people talking to me about several things. I don't think any of the questions is an idea of mine. So I'll start by Jordan type. So if I have an Artinian algebra over a field K, and if I have an element in A that is nilpotent, I take a module over A, finite module, dimension over K of M, I'm going to say is N, and I consider multiplication by L, which is an endomorphism from M to itself, and the Jordan type of L in M, which denoted by P, L, M, is the partition of N, giving the sizes of the Jordan blocks of multiplication by L. And to see this in an example, and also to help us understand how we usually compute and how we usually deal with the Jordan type, let's take this algebra. I'm taking the field of polynomials in x and y. I'm modding out by x squared, x, y squared, y 5. And I can look at this algebra. This is very simple algebra. It's defined by monomials, and it's very easy to write down basis for this algebra, just in terms of monomials as well. Y squared in degree 3, I only have y3 now, and in degree 4, I have y4, and this allows me to quickly compute the Hilbert function of this algebra. This is 1, 2, 2, 1, 1. It's a graded algebra, but it doesn't have to be. Jordan type is defined for any algebra, but I just chose a graded one because it's simpler. And I'll take L1 to be x plus y. If I do this, and I want to compute the Jordan type of L1, what I usually do is take 1, to start with 1, and see where multiplication by L leads. So this will go to x plus y. X plus y, then, if we multiply again, since x squared is 0, it's going to give us just 2xy plus y squared. If I multiply again, I'll have y cubed. If I multiply again, I have y4. And if I multiply again, I have 0. And then I still don't have enough elements here to form another basis of A, but I can add x to this diagram and see what happens to x. X goes to xy, and xy goes to 0. And now I have enough elements, and I have what we know as a Jordan basis. And the reason, sorry. So the reason this is a Jordan basis is that we can use this basis, reordering it. So y4, y cubed, 2xy plus y squared, x plus y, 1, and then in the other string, xy and x. Yes?
Sorry to tell you now, but it's hard to see below the middle of that board.
Oh, yeah, you're right. Okay, let's try to. So I'll just not use that word. Thank you. So y4, y3, 2xy plus y squared, x plus y, 1, xy, x. And again here, y4. And I know that y4 goes to 0. y3, I know that y3 goes to y4. 2xy plus y squared, I know that this goes to y cubed. X plus y goes to 2xy plus y squared. 1 goes to x plus y. And xy goes to 0. And x goes to xy. Okay, so this is just to take the definition as it is and show you that when we have a Jordan basis, we can build a matrix for this map as a linear map. And from here, we know that the Jordan type of x plus y in A is 5 from this block and 2 from this block. Okay. Fortunately, we don't have to build a matrix every time, because if we look at these two sets of strings, we have the information here already. So the first string has exactly 5 elements. The second string has 2 elements. So it's enough to have these sets of strings to compute the Jordan type. I just do this for fun, but I do it once. I won't repeat it. So we can look at what happens to another linear form, x. So again, I see what happens to 1. 1 goes to x, but x goes to x squared, which is 0. Y goes to xy, and xy goes to 0. Y squared goes to 0 directly. Y cubed goes to 0 directly, and y4 goes to 0 as well. And from this, we already know that the Jordan type of x in A is going to be 2 from this string, 2 from this other string, and then 1, 1, 1. So 2, 2, 1, 1, 1. And still another example, which might fit here. I'll try it. 3 x plus y squared. So far I've tried linear elements, but they can be anything in the maximal ideal. And what happens to this? I'll start the string here. 1 goes to x plus y squared. But then when we multiply again by this element L3, well, x squared is 0. Y squared is also 0. So the only thing that survives is y4. And y4 goes to 0. If I take another element here, y goes to x, y plus y cubed, and this goes to 0. Y squared. Now y squared is interesting because it does not go to 0. Y squared goes to y4. And finally, y cubed goes to 0. So thing is that what we have here is no longer a Jordan basis, because there is an element here that's not in the kernel. So we don't build a Jordan canonical form from this basis. We call this a pre-Jordan basis. And the condition is that we don't ask that the ends of these strings are kernel elements. We don't ask that all of them go to 0. We just ask that if they don't go to 0, they just go to the space spanned by the previous strings. So we're doing them in order, and we're asking. Okay, the definition is slightly more detailed, but the main idea is this. And the thing is that from a pre-Jordan basis, we can build a Jordan basis. Usually it's not as nice as the pre-Jordan basis that we built, and that's why we like pre-Jordan basis. But for the purpose of computing the Jordan type, it's irrelevant because the Jordan basis will have exactly these kinds of strings. So the elements will be changed, but the strings will have exactly the same shape. And so from this pre-Jordan basis, we can say that the Jordan type of x plus y squared is 3 from this first string, 2, 1, 1. Okay, so no. Yeah. Yes. Yes. So it's enough that you have a pre-Jordan basis to get the Jordan type, because from a pre-Jordan basis you can build a Jordan basis which has the same kind of strings. So the strings will have the same length, and from a Jordan basis you print this Jordan canonical form. So you don't lose the information. Yes, Larry. Let me think. So this guy will be the same, and then we'll have something here. I'm not sure. I haven't thought about that in terms of matrices. No. It's okay. I'm not sure. I'd have to think about it and make a few computations on matrices and examples. Yeah, and it might be a very simple thing. I'm not sure how.
You just subtract a multiple one line from another line.
So thinking about it, I think you must, because what Tony's saying, we're just doing Gauss on the matrix when we're doing here. So if we want to clean that part, all we'll have to do is just Gauss operations, and then we have matrices that do that for us. So it's
upper triangular. Upper lower triangular.
Mm-hmm. Yeah. Yes.
In this example, you just gave, is
the only thing that you need to do to go from 3 to Jordan to work is adjust the y squared?
In this one, yes.
What would you add to it to make it work?
I'll probably subtract something. Let's see. I know that, let me go here. Sorry. So I know that x plus y squared times y squared is y4. And that means that x plus y squared minus y4 is 0. So x plus y squared minus, and I know that y4 is just L squared. So I replace it, sorry, x plus y squared minus x plus y squared, sorry, this is not squared, here it's squared inside. X plus y squared is 0. So I'm just replacing y4 by how I know I got it. And then I just factor, and I have the element I want. So x plus y squared times y squared minus x minus y squared. And this gives me x. And this gives me x, yes. I think x times x plus y squared. So this is an element that could replace this one. And I think we're fine. Okay. Thing is that, for instance, in this case, I would have an element of order 1. I don't like that much. I like to have elements in the orders according to the Hilbert function, because it's easier for me to think. So the Jordan basis will be uglier for me, nicer for the matrix. Since the matrix doesn't talk, I impose what I do with them. But this is what you were asking, Brian. Okay. I think I was here. So there's some things that we can get from this example. One of the things is looking at what happens to the Hilbert function. So the Hilbert function is, 1, 2, 2, 1, 1. We can reorder these elements and make this into a partition. Two, 1, 1, 1. And we can conjugate this partition. That means that we're taking this diagram and we're changing rows by columns, and we get this other partition, 5, 2. And what we see here, so we call this the conjugate of the Hilbert function. What we see here is that the Jordan type of x plus y in A is the conjugate of the Hilbert function. Okay, we'll see why this is important later. But these two coincide. I don't know if the Jordan types are still visible. There's one that's lost, where I put, so I can write it again. P of x plus y is 5, 2. Okay. And there's another thing that that is nice in this example as well. Which is null. here's my colors, which is that we have the Turin type of x plus y, which was this partition. We can draw this partition in this way. I'm just drawing the line and then making the next row start with where the other finishes. We can do the same for p of x plus y. We have that it was 3, 2, 1, 1. So we, oh, sorry, I want to change colors. X plus y squared, sorry. So this, and we can do the same here. So we have a 3, we have a 2, and we have a 1 and a 1. And we have the partition of x, which was 2, 2, 1, 1, 1. Sorry, 2, 2, 1, 1, 1. We can do the same. 2, 2, 1, 1, 1. And if we put these diagrams together, we can fit them one over the other very carefully. So 1, 2, 3, 4. So I can put this one here. I can put this one right below it without overlapping any boxes. And I can put this one below the second one, again, without overlapping any boxes. Okay. And what this is saying us is that under an order that I'll define just now, p of x plus y is greater, well, dominates p of x plus y squared, and this dominates p of x. It's just a visual way of looking at what I'm going to write down here. So if I have two partitions, of the same number n, I'll say that P dominates P prime if and only if for any partial sum that we can have with the first elements of P, this is greater or equal than the corresponding partial sum with the elements, the parts of P prime. Okay? This just looks a bit more ugly than this, so I like the picture. But so that translates in being able to perfectly fit one below the other without any overlapping. Sorry? I didn't get that. Majorization? Okay, I didn't know that name. Thank you. Okay, so for some properties of Turin type, so this is result with Tony and Chris. So first of all, if A is an Artinian K algebra, M its maximal ideal, M is a module over over A. There is a Zariski open dense set U in the maximal ideal such that if L is an element in U, then the Jordan type of L in M dominates the Jordan type of any L0 in M. And we call this, and by this I mean this Jordan type, the generic Jordan type of M. We denote it by PM. So another consequence of the semi-continuity is that if MT is a constant length family of modules over an Artinian algebra A, parameterized by T, and T0 is an element of T, then there is a neighborhood U of T0 such that P of MT dominates P of M T0 for all T in U. Okay, so this dominance partial order, Jordan type is semi-continuous with respect to this dominance partial order. We have these two results, and I think there are two main strengths of Jordan type. Of course, this is open for debate, but this is how I see it now. So it is a finer invariant than the Lefschetz properties. And the second one is that it allows us to extend the Lefschetz properties two non-graded algebras. And so why is it a finer invariant? This is a result from Watanabe, 2003, and then again Harima, Maeno, Morita. I don't know if I'm saying the names correctly, I'm sorry. Numata, Wachi, and Watanabe from their book. So if A is Artinian, standard graded, and L is an element of A1, so it's a linear element in A, then L is strong Lefschetz, if and only if the partition, the Jordan type of L in A is the conjugate of the Hilbert function, which is what happened to x plus y in the example. And L is a weak Lefschetz element, if and only if the number of parts in the Jordan type PLA is the Sperner number of A, and the Sperner number of A is the maximum of the Hilbert function. Okay. So knowing the Jordan type of any element, we know if that element is a strong Lefschetz element, a weak Lefschetz element, or none of them. And this is why Jordan type will be a finer invariant. Yes. Sorry, it's really lousy. It allows us to extend the Lefschetz properties, and Lefschetz should not have it's not a T. Lefschetz property to non-graded algebras. The first point is that it is a finer invariant than the Lefschetz properties.
Are you gonna do two now, or?
Yes.
Oh.
I'll try to, at least. So, extend Lefschetz properties to non-graded case. Okay, so what we know, and this is also, I'm not going to repeat the names, but all of the above, W from 2013, and then joint work with Yaruino and McDaniel. We know that if A is graded, but possibly non-standard, but with A0 equal to the field, and if M is a finite length, finite module, L in A1, then the Jordan type of L in M is dominated by the conjugate of the Hilbert function of M. And we also know, what should I write? We also know that if A is local Artinian with K is A over M, and M is a finite module. If L belongs to the maximal ideal of A, then the Jordan type of L in M is dominated by the Hilbert function. So here we don't have a grading, but we can consider the M-adic grading by the conjugate of the Hilbert function we obtain when we consider the M-adic grading of A. Okay, so we force a grading not on A but on the associated graded algebra, on M, on I don't know if we can call it the associated graded module, but so we have these facts, and we can extend. I have to stop here. So if we have a local Artinian algebra and we have L in M, we can say that L is weak Lefschetz if the number of parts in the Jordan type M is the Sperner, not M, sorry, this is A, the Sperner number of A, and we can say that L is strong Lefschetz if the Jordan type equals the Hilbert function of A, the conjugate of the Hilbert function, of course, again, we're considering the Hilbert function given by the M-adic order. Yes, Graham?
The Sperner number, you mean of the associated graded again? Yeah.
Yes, yes. So I take the Hilbert function of the associated graded algebra. That's how we can build a Hilbert function from a non-graded algebra. And the Sperner number will just be the maximum of that element. And I'll have to stop. Sorry, I promised problems. I haven't got to the question almost, but I have to stop here. Thank you.